Hmm. Amy, you still there? Bye, sweetie. Okay, hi MATH7502, welcome. 5 in the afternoon, we're recording, I think so, in 5 in the afternoon in Brisbane, a bit earlier in most of the elsewhere places. Nobody's here in Fiji, I believe, right? Do we have a student in Fiji? No. Okay, any questions before we pick up? No. Okay, so we're here in week 6, September 7th. Next week you've got the quiz. And this is going to be actually an exciting lecture. So I hope you'll see it as I do. Simply because we're going to get to do least squares and some data fitting, ideally. So we're really going to touch the heart of things. So let me just start by reviewing actually the last lecture very briefly. I'll just do this extremely quickly. So we spoke about, this is what we did pretty much last week. We spoke about linear transformations. We spoke about vector spaces. And you saw vector spaces in the practical. Sam showed you quite a bit of other examples of vector spaces. But of course, when we're speaking about a matrix A, then the two important subspaces of the vector space are the column space and the null space. And the null spaces, they're each important in their own right. So the column space is important because it's the set of vectors that are spanned by linear combinations of the column. So when you look at the column space here, then these are all of the vectors that you could reach with the mapping A times X. That's a column space, sometimes called the range or the image of the matrix. Okay, and the null space is a vector in a, or the kernel, sometimes the null space called the kernel, the vector space in a different dimension. It can be with vectors of different lengths, etc. And these are all the vectors that put you at the point 0. So if you say that a matrix has a 0 null space, what does it tell us about its column vectors? If a matrix has a 0 null space, what do we know about the column vectors? So they're independent, okay? So as I said, they're independent. Now, you will, if you're speaking about, and there was another answer that's full rank. So full rank is a kind of another term that you'd say that the matrix has a zero null space if we're speaking about skinny matrices, right? I mean, if the matrix is skinny or fat, it tells us nothing about the elements of the matrix. It's just kind of the dimensions. But if you're speaking about skinny matrices, then zero null space is also full rank. If the matrix is fat, meaning that it has more columns than rows, then, well, it can actually not have zero null space, okay? But it could still be full rank because the rows might be linearly independent, okay? But actually, most of our data matrices that we treat will be skinny, and you'll see that in the applications today, okay? And then we spoke about linear independence, which is intimately related with a zero null space. And we spoke about a basis. So a basis is a set of linearly independent vectors that spans a vector space or a subspace, okay? So when you say basis, you always mean a basis of something. So if you have a basis, you have just the right number of vectors that you need to get to any point in the vector space in a unique manner. We spoke about that. And I didn't say a whole lot about the four fundamental subspaces, and actually won't say a whole lot, but actually this figure, which in this case it's taken from the Introduction to Linear Algebra book, page 197, although it appears in several other places, pretty much summarizes kind of the big picture that we have. So we're taking an M by N matrix, okay? An M by N matrix. And if we're speaking about an M by N matrix, then we have vectors in Rm, and we have vectors in Rn, okay? So the vectors in Rm can be the column space, also called the range, okay? But we can also have a different, a different subspace of Rm, which is the null space. Now, it turns out that these two subspaces are actually orthogonal. We still didn't, in this unit, didn't speak of orthogonal, but you already know what that is. So that means that every vector here is orthogonal to every vector there. That's just 90 degrees, okay? Now, the dimension, what's the dimension of a vector space? What's the dimension of the vector space? Dimension of the vector space has to do with how many vectors are needed in a description of the vector space. It's the number of vectors in the basis of the vector space, right? That's a dimension of the vector space. So even though Rm is the whole set of vectors that we reach when we apply the matrix A to some vector X, then the dimension of the subspace, which is a column space, might be lower, and that will be R. So that is that one integer quantity, the rank, that is associated with a matrix, okay? So the dimension of the column space will be R. And in a sense, the null space is the complement, the null space of A transpose in this case. That's a null space of the of A transpose, okay, that's what it is the complement of this column space. Now, when we say complement in the notion of sets theory, then you can take the full thing, you can take Rm, and you can say, if this is some set, okay, if this is some set, then this is another set. And then if I'm saying the null space of A transpose is a complement of the column space, then that means that their union is all of Rm, and they are disjoint. Disjoint means that two sets are disjoint. That means that their intersection is the empty set. But are these two sets really disjoint? Are the column space of A and the null space of A transpose disjoint in the set theory notion of things? Is there no vector that is in the column space of A and in the null space of A transpose? Are they disjoint? Can you find a vector that's either in the column space of A or in the null space of A transposed? You don't need to know a whole lot about this, just one property of vector spaces and subspaces. What vector has to be in a subspace? What vector? The 0, right. So the 0 is both in the column space of A and in the null space of A transpose. So they're almost disjoint. From a linear algebra perspective, they're effectively disjoint, but no, they're actually intersected that 1, 0 that's here. Okay, this is of course a schematic description. This is not a geometric description. Okay, and the dimension of A transpose is M minus R. Now, if we go into the other associated space with the matrix, and that's Rn, okay? That's Rn. So Rn is the number of columns. We're speaking about, again, an M by N matrix, okay? An M by N matrix. So the row space of A, the row space is like the column space of A transpose, okay? So it's all the possible linear combinations of the rows that you can do, okay? That's what the row space is. And what is sometimes called the fundamental theorem of linear algebra is the fact that the dimension of the row space is R, okay? Which is the same as the dimension of the column space. So these two R's here, this R on the right and the R on the left, these vectors live in completely different worlds. Remember, N might not even be M. I mean, M will be M if this is a square matrix, but the matrix doesn't have to be square. However, the number of linearly independent rows is like the number of linearly independent columns. Okay? The number of linearly independent rows is like the number of linearly independent columns. And again, the complement, and I'm putting little quotes over the complement because these two vector spaces still intersect at 0, of the row space is the null space. Okay, and that has dimension N minus R. Okay, so if we're speaking about a 0 null space, what is R? We like 0 null space because it means linearly independent columns. What is R in a 0 null space? What is the integer R? What is the rank if our null space is 0? And again, when we say null space is 0, what we mean is that it only has a 0 vector. That this set is actually just going to be this point, 0. What is going to be R? What is going to be the rank if we're speaking about a 0 null space? I'm seeing all kinds of things. I'm seeing capital M1, M full rank. But what if I want the dimension of this thing to be 0? What should I put for R here? So there was an answer full rank indeed, and full rank in this case means N actually, N, right? I said there N. So a 0 null space means that the rank is N. It means that all of the columns are linearly independent. Okay, that's the case. All right, so there's a lot happening here, but there's not. And by the way, these two spaces are also orthogonal. Okay, so the row space of A and the null space of A. Okay, so these are the 4 fundamental subspaces. I'm spending now more time on this than I did last week. Okay, this last thing, change a variable of integration. This is not in the quiz, and I might do it after the lecture of the quiz. So, but we'll see how far I get with least squares data fitting today. Okay, but it's still something that I'd like you to see, and you should see as part of this course. Okay. So then we moved on to Unit 4 in the core linear algebra, and we've dealt with orthogonality. We still haven't done projections. That's what we'll do today, and we still haven't done least squares. And we start by saying that two vectors are orthogonal. Well, they're orthogonal if their inner product is 0. Fine, we got that. And we can call a collection of vectors orthonormal if their norm is going to be 1. Okay, so they're all already kind of normalized. So if you plot them, they all lie on the unit sphere in a sense, right? That's kind of on the unit surface, on the unit ball. That's where they would lie. Okay, and their inner products are going to be either 1 if they're the same vector, or 0 if they're or not the same vector. Okay. We also showed that orthonormal vectors are linearly independent. Okay, and then we spoke about orthogonal vector spaces, which I just told before about. Okay, now we got to the Gram-Schmidt procedure. And we're actually going to implement the Gram-Schmidt procedure, and then we'll see its relationship to a central factorization, one that many people think are, in a sense, more important than the LU factorization. It's going to be related to the QR factorization. So we'll get to that. So what did we do in the Gram-Schmidt procedure? Well, first of all, let's just read this as an algorithm. Then we'll look quickly at the steps we did. Then we'll understand the algorithm. Then we'll, because this is where I stopped, and then we'll actually implement it, and then we'll move with it more. Okay? So very quickly, what's here? So we've got n vectors. Are these n vectors, or are these vectors of length n? So by this, what I mean n vectors? These are vectors, each with n coordinates. Okay? How many do we have? We have k of them. We have k of them. Okay, k can be 2, k can be 1, k can be 700, even if n is maybe just 3 or 4. But you know, what you should think about this, so when you see this thing as a data scientist, then think of, then think of k people that you're taking observations from. Okay, k people, and you know, k is maybe the population of, do you want to do Australia or China? I don't know, either 25 million or so, or 1.4 billion, something like that. Okay, that would be k. And n would be maybe 2,000, 3,000 is a number of features per person. Okay, so this is how you can think of this in terms of data, just to kind of think of this, you know, n and k. But, you know, maybe it's different. Maybe n are pictures, and then, you know, a picture has many, many pixels, so the vectors will be much bigger. Okay, let's get back to the linear algebra. So the first thing we do is we actually take this vector qi tilde, and then we're indexing 1 to k, and qi tilde is going to be the ith vector after we subtracted from it these things, and we'll see in a second what this really does. Okay, and then qi tilde is really, you can call qi tilde the innovation. So qi tilde is going to be the new direction that has still not been spanned by the previous vectors. Okay. Now, if I equals 1, then qi tilde is just going to be vi. But otherwise, you're going to subtract from it these guys. Now, if qi tilde equals 0, then what we actually find is that qi tilde is a linear combination of the previous vectors. So we quit. Why do we quit? Because we say, hey guys, the vectors actually v1 through vi, the ith iteration, are linearly dependent. And we actually know how. Because just look here. qi is a linear combination of then vi and the other previous q's. And all those previous q's are linear combinations of the other vi's. Okay? So we quit. By the way, there's a different version of Gram-Schmidt that at this point does not quit. It just kind of puts the vector on the side. It kind of moves that vector on the side and says, hey, you, Mr. I, you're linearly dependent. You linearly depend on the other vector, so I'll put you on the side. Okay, so there are all kinds of different versions of Gram-Schmidt. But in this version, we quit. There's also the version that just assumes that the given vectors are linearly independent. And in this case, you don't even need step 2. Okay. Then you go to step 3. In step 3, we just normalize qi tilde. Okay. But if you don't have step 2, what can happen in step 3? If you don't have step 2, what can happen in step 3? What can happen in step 3 if you don't have step 2? Either my question is very hard today, or everybody very sluggish, or maybe the internet is sluggish, or maybe, what are you doing here in step 3? If you don't have step 2, you're dividing by 0, right? So what happens if you divide by 0? Sparks. You get like sparks from the computer, everything crashes, you get a blue screen. I don't know what happens. Maybe your punch cards are flying out, whatever, you don't know, okay? So we don't want to do that, and that's why step 2 is there. But you will be able to do it without step 2 if your preconditions were that the vectors were linearly independent. Okay, just so we see that. All right, so this is how this algorithm works, and we actually did it here. So we had here two vectors. These are these are again 3 vectors, like vectors of length 3, and there's 2 of them. So n equals 3, k equals 2. Okay, we had these 2 vectors, and that was v1 and that was v2, and q tilde was v1 minus nothing. Okay, because this is nothing in the first iteration, and q1 is just a normalized version of that. Okay, and then in the second iteration we subtract this guy. Okay, so let me go a second to the scratch pad, and we see what this thing does. Okay. So let's see. Okay. So in the first iteration, what we took v1, now is this guy, and all we did is we kind of normalized it. So, you know, we made it maybe this, okay, because maybe this is the unit ball, okay, maybe this is normal. So that we took v1. That's all we did with v1. And then we took the vector v2, which was maybe pointing like maybe, oh, that's a bad example, sorry. Let's put v2 to maybe point like here, okay? v2, let's say that this guy is v2, okay? We took v2, and we said that q2 tilde is v2 minus q1. This guy, this green guy here is q1, okay? That was our first orthonormal vector that spans the same set of vectors of the v-span, okay? Times the inner product of q1 and v2, okay? So this is a scalar, okay? The inner product of q1 and v2 multiplied by q1. Now, what this thing did is this expression here that we subtracted from v2 is actually a multiple of q1. You see, it's a multiple of q1. It's this thing. This is a scalar. That's an inner product. It's a multiple of q1. So it lives someplace on this q1 line. It lives someplace on this q1 line, okay, on this q1 direction. It's a multiple of q1. And what it does is actually it's exactly this multiple. It's the projection of well, it's up to that. It's the projection of v2 onto q1. Okay. So what we've done is we've then removed from v2 this red component. So that's this red component that we've removed. So what we have here is basically the vector that we get is it's going to be something like this, and that's this guy. Okay, that's this. And that's q2 tilde. And then the next step is just to take, let's make it green, q2 is q2 tilde divided by the norm of q2 tilde. Okay, so then we normalize it again. So basically all we got, it looks like this a bit silly. It says, okay, hey, I gave you 2 vectors, v1, v2. In this case, they're just 2 vectors the way I'm drawing them because they're on the plane. And what you get is q1, q2, but they're an orthonormal set that spans the same space spanned by v1, v2. But we'll see that computationally this is quite important, because then it allows us to describe. So now we can describe any vector that is described in terms of v1, v2. We can describe it in terms of q1, q2, and they're an orthonormal collection. And then if there was a third vector, now any third vector, if there was, now I'm talking about 2 vectors. So let's say this was now the third vector, v3, okay? So v3, what I'm going to do is I'm going to do q3 tilde, okay? It's going to be v3. q3 tilde is going to be v3 minus q1 transposed times v3. So that's that inner product times q1. So this is the description of this v3 in terms of q1. Okay, that's what this is. Minus the Q2 transpose inner product V3 times Q2. This guy, this, let's say this purplish pink thing that I'm highlighting here, okay, is the description of this V3 in terms of Q2, which is just going to be a very little small description. It's just going to be something like that. It's going to be a little thingy there. Okay. Now the thing is that unfortunately, what I'm going to get here now, because these are two vectors, I'm going to get a 0. This thing is going to be a 0, and I'll conclude that V3 and V1 and V2 are linearly dependent. So I actually know that by doing this type of combination of the original vectors, I can get V3. So then I'll stop. I'll say, hey, V3 doesn't play. In a different version, I might just push V3 aside and say it's a linear combination of these two. Okay. So that's that for starters. And now let's implement this. In a general setting. So let's just make seeing this implemented might be useful kind of as a general thing. Okay. Let me just, this didn't run because I just do using linear algebra. And then of course what we get here is if we put these two vectors Q1 and Q2 in some matrix Q, this is an orthonormal matrix as we saw here. So the first column has norm 1, the second column has norm 1, and the two columns are orthogonal. Okay, Q transpose Q is then obviously the identity matrix. This is the identity matrix. Okay. Okay, so and we see that Q transpose Q is the identity matrix, and is Q inverse Q transpose, then the answer to that is, let me just put it, only if K equals N. Okay, so only if Q is actually a square matrix. Okay, so let's implement this Gram-Schmidt procedure. So let's make a function, and the reason I want to do this is you need to understand there may be two key algorithms in linear algebra. The one we spoke about 2 weeks ago, and many of you have done in different courses in different years, and that is Gaussian elimination. That's kind of the central one that's taught. But the second one is Gram-Schmidt. And the fact is that you can do almost anything that you can do with Gaussian elimination, you can do with Gram-Schmidt. Almost everything, or many things. Okay, you can solve system of equations with Gram-Schmidt, etc. We'll see how. So it's actually a very powerful concept in algorithm. Now, again, I must say that the implementation that we're seeing here and that we're going to do is not the implementation that is the robust, numerically stable implementation. That's not what this course is about. Okay, so that should be clear. That's the case. Okay, so let's do function my Gram-Schmidt. Okay, and what this function gets is a vector list. Okay, it gets a list of vectors. Okay, so when I say list of vectors, let's before we actually, sometimes when you implement a function, it's good to even kind of write the test even before you finish implementing it. So call this the V list, the vector list. It's going to be an array of vectors. It's going to be the array V1, V2, V3, and let's take V1 to be 1, 2, 3, and V2 to be -4, 0, 2, and V3. So I'm taking here in this example K equals N, okay, and V3 is 2, 1, 4, for example. Okay, so here I'm taking K equals N equals 3. Okay, and then what our function, which we still didn't implement, does is my Gram-Schmidt on this V list, and what we hope is that it'll give us, I didn't run this yet, my Gram-Schmidt, okay, and what we hope is that it will give us, this still doesn't work, right, but that it will give us the vectors Q, okay. So let's just do here. So what we can do, I guess, I'm not sure what we're doing, but let's see. You'll help me if needed. So let's take n to be the vector list, the first element of the vector list, the length of that first element. So our assumption here are that all vectors in vector list are of the same length. We're not going to do error checking. And k to be the length of the vector list. Okay. Okay. You can just debug a bit if you want. You can do show n and show k, run this and run this again. So n equals 3, k equals 3 in this case. Okay. All right. I'm going to delete these shows, or at least comment them now. Okay. We don't need that. Okay. Now, what do? We do a loop, like most of these algorithms. Okay. And this loop is going to loop for I going 1 to k. Okay. So we do for I in 1 to k. That's simple. Okay. And then let's do q tilde. This is q tilde. Okay. qt is like our q tilde. So q tilde, if we remember this guy, okay, it's going to be the kth vector. It only depends on the previous q's and on the current VIs. Okay, so let's be a bit brave. Okay, so let's do here. It's going to be VI minus, and here is going to be this thing here. This SSSS is going to be this summation which we have here. Okay, so let's look at the summation. We're going to have some other index, say j. J will need to run from 1 to I minus 1. Okay, j will, but we have to be brave, and you know, first iteration this thing might be 0, right? Remember, we subtract nothing, right? This sum is an empty sum, but let's just hope it all works, and if not, then we put some conditional statements, some if for the first iteration. So what we want here is we're going to do something for j in 1 to I minus 1, okay, and then we're going to sum these things. Okay, so what we're going to do each time is we're going to do here in this SSSS thing here is exactly going to be the QJ inner product with VI multiplied by the vector QI. Okay, so this won't work yet, but let's do it. Okay, so what we're going to do is we're going to do QJ inner product with VI. Okay, so this thing should be a scalar. This is an inner product of QJ VI multiplied by QJ. What is this thing that I'm highlighting here? I mean, first of all, I didn't define Q, but assume Q as a vector. So what is this thing? What is this a vector or a scalar or a matrix? What is it? Thing that I'm highlighting. It's a vector. It's a vector, right? Okay. So it's a vector, and we are going to have here this comprehension is going to be an array of vectors, and we assume that we can sum an array of vectors, and you can. So when you do a sum, apply the sum function to an array of vectors, you're just summing up the vectors. Okay. But of course, Q doesn't exist. So let's create Q. Let's make Q. Just write it like that. Let's make it an empty list. Okay. So, and you know, start empty. Okay. We could also have initialized it with zeros, etc. Let's just start empty. Okay. That's just Q of t. What's the next step? Well, the next step was maybe if Q of t equals zeros of n, then you know, maybe do an error linearly dependent. Okay, linearly dependent. Okay, something like that. Okay, that was our step 2. And what's the next step? What is going to be the actual, let's call this QI. What's going to be the QI? What do we do after we've done this step? What's the next step? Look here. Add normalize, right? Or no, add but normalize, right? So QI is going to be QT divided by norm QT. That's QI. And then, you know, let's push it to QI, something like that. Okay, this is not necessarily the most efficient implementation because you're starting with an empty array. It's in many ways not, okay, but that's okay. You're starting with an empty array Q, and every time this kind of appends QI to the end of that array, and when you do that, sometimes the computer needs to reallocate and things like that, but that's okay. Now, this here too is not so good because QT, to say that it's zeros is maybe not the best thing because, you know, sometimes it'll be very close to zeros. It's not going to be exactly zeros. So the better way to do when you're doing things numerically is to say if norm of QT is, say, less than 10 to the minus 8. This is better. Okay, so this is like almost 0. That's not critical. Okay, and then as return value, we can just write Q. Return Q. Okay. It would have been better to maybe call this thing the Q list, but then I need to go and I need to put Q list here and here. That's okay. So this looks a bit kind of more too many symbols, but that's okay. Now, of course, in the first iteration, I equals 1. So this is going to be the empty list because J goes from 1 to 0, okay? But when you sum the empty list, that should work because if you do sum the empty list, it should just, well, I thought it would work. Maybe it doesn't. Okay, this might not work. Okay, it might not work, but we'll fix it in a second, okay? Yeah, we'll see in a second what this does. Let's see. Okay, let me keep that. So here is a function. Let's try to run it. It seemed to have run, but what I get here is I'd want to return Q list. Okay, return Q list. And V not defined. So where is this V not defined? So I'm getting an error V not defined in Gram-Schmidt line 8. So I'm going here to line 8 and V not defined. Well, V not defined because V needs to be the element from vector list. Okay. So let me just, so these things look, I'll just call this thing V, I'll just call this thing Q, and then this is Q and this is Q, and things look mathematically a bit cleaner, even though programmatically things are a bit kind of, and I'll delete these shows because we're not worried about that. Okay, let's run this again. Let's give it a go. Now vector list not defined. Oh, V. Run this again. Run this again. Okay. So we have some dissatisfied customers, probably with this first iteration. Okay, probably with this first iteration. So let's just to debug, so to see what's happening, then let me copy this here and let's call this the reduction. So I'll just call it the red. Okay, is this thing, and then let's show it. Okay, and I'll run this again. And it never gets there, okay? It never gets there because this thing fails. This thing fails. Okay. So what are we supposed to do? Well, there are different things that we can do. We could have done different things. One thing we could have done is we could have started I going from 2 to k, for example, and the first iteration we do ourselves. So what are we going to put in the first iteration? Well, we're just going to we'll check if norm of V1 equals, or sorry, is less than this tolerance, which we kind of arbitrarily chose, then again, say error linearly dependent. What does it mean that a vector is linearly dependent? One vector, how can one vector be linearly dependent? How is one vector a set of linearly dependent vectors? That's actually an important question. How is one vector a set of linearly dependent vectors? Well, but there's only one vector, so it's combinations of other vectors, but there's only one. So it's zero, exactly. So a single vector is still so a set with a single vector is still, or a collection with a single vector is still a linearly dependent set if that vector is zero, okay? Because any combination, any inner product with it, any combination of it, right? You don't have to have that combination will yield zero, even if, so any scalar alpha that you multiply times that vector, it's not an inner product. Any scalar that you multiply times that vector is going to give you the zero. Okay, so that's kind of this thing. So then we assume we pass this. So what do I put here? I put V1 divided by the norm of V1. Okay, so so start with first Q. Okay, so the first Q already exists. Let's hope this runs, but maybe something else didn't work and I just made another mistake. Let's see. Okay, so let's run this. Oh, that looks kind of better. And we got here some debug on this red. So we don't need this anymore. Let's close this. Now we could have circumvented that problem, but so we could have done it in a more elegant way such that this sum would not be zero. But I'll leave that to you to think about if you'd like. It's not critical though. It's only if you're. And this is now our Q list. That's our answer. So let's check. So that's our Q list. Okay. Q list is this thing. Now let's make what we would like is, first of all, let's apply norm to Q list. So this is the norm function. This is not a matrix. This is a list of vectors. You see, it's an array of arrays. Okay. You can always put a list of vectors of the same size in a matrix, and if you've done a lot of MATLAB, that's always what you do. But actually, sometimes you actually want to think of a collection of vectors. So this is an array of arrays. Okay. So that's what it is. So norm Q list, norm applied to Q list should give us 1, 1, 1. Okay, they're all norm. Now, if I do Q list I, Q list, let's say I, which is 1, inner product with Q list 2, what should I get now? What is the 0, right? Because they should be, and that's a 0, right? And the same will happen if, say, 1 and 3. The same would happen, say, with 2 and 3. Okay? And if I want to put them in a matrix, then what I can do is vcat on Q list, ... Let's see if this works. No. hcat of Q list. And that puts them in. So this ... is called the Splat Operator. This thing that we did is equivalent to doing, it's just like doing hcat of Q list 1, comma, Q list 2, comma, Q list 3. That's what this splat, okay? Splat operator does, okay? It kind of takes the argument of an array and puts them all as inputs. Yeah, so there's a great question by, I just don't name names, because this is, we can then be haunted down. There's a great question by Jibla, and that question is, so if we input unit basis, we will get unit basis, and the answer is yes, okay? Because the innovation, so you put in an orthogonal collection into Gram-Schmidt, and if you put anything orthogonal into Gram-Schmidt, there'll be no innovation every time. Okay, so the the first vector v1 is going to be completely orthogonal. V2 is going to be completely orthogonal to v1, and it'll be completely orthogonal to v3. Yes, so you can try that later. Okay, so we were just here, and we called this, say, the matrix Q, and then Q transpose times Q is going to be the identity. What's, by the way, the inverse of Q? It's Q transpose. Yeah, it's Q transpose. Right? So inverse of Q minus Q transposed is going to be all zeros. Okay, that's it. So you did Gram-Schmidt. Questions? I mean, now is the time to start asking why this is good for, and we'll see how this plays a role in quite a few things. Okay. All right. So just a few more things about matrices with orthogonal columns, such as this Q that we got, okay? So here we call it A, but also often we'll call a matrix Q. So we know that Q transpose times Q is going to be the identity. We just saw this, okay? And so these things that you see here, we've just seen and we've spoken about before, but I don't think we've seen properties 1, 2, and 3. Now, properties 1, 2, and 3, their story is as follows. So, by the way, A, you can call it an orthogonal matrix if it's square, or just a matrix with orthonormal columns. It's very confusing because you say orthogonal, but you actually mean it has orthonormal columns and it's square. So again, an orthogonal matrix, that word is reserved for square matrices with orthonormal columns. But in the Gram-Schmidt, you could have had, you know, we could have had 4 vectors. We could have had like vectors which are like in R4, like these ones, okay? These are now 4 vectors, and you know, their norms are still 1 or numerically 1, but the matrix Q in this case, so if I go here, the matrix Q is no longer square, okay? You see it's 4 by 3. So in this case, the inverse of Q is not Q transposed, but still Q transpose times Q is going to be the 3 by 3 identity. Okay, so just keep that in mind. So A can be square or not, but no matter what, when you apply that transformation A or Q onto a vector, then you're actually preserving norms and you're preserving angles. Okay, so you're preserving the norm, preserving angles. So let's see this quickly. Okay, we'll take a break just shortly after. We'll see it on the notepad. All right. So let's call, you know, A with orthonormal columns. Okay, that means that A transpose A is the identity. But just so we know, if A is n by k, then A transpose A is the k by k identity. Okay, so and k must be, by the way, k must be less than or equal than n. So k must be less than or equal than n because we proved that you cannot have more than n orthonormal vectors, right? Because otherwise they'd be linearly dependent, right? So orthonormal, we proved that last week. Orthonormal, a collection of orthonormal vectors is linearly independent. All right. So if you do, if we want to look at now, the key is to look at AX transposed AY. Okay, this is a key. So this is let me write what this is. This is the inner product of AX and AY. I mean, I write it because what? Because we're applying A to X and we're applying A to Y. Okay, applying A to X and we're applying A to Y. So then comes these kind of fun calculations. So how can I write AX transpose? Well, this is going to be, by the way, a huge thing in the next 2 hours and the next continuation. A B transposed equals B transposed A transposed. Wrote it so horribly. So it's I mean, it's as though I didn't know that I'm going to run out of space. That side of the iPad just surprised me. So B transposed A transposed. Okay. So applying the same rule here, and this rule will be applied all the time. It's X transposed A transposed A Y. What is this? Chat disappears when I put this. It's identity, right? And you know what dimension of identity? Well, it's this dimension of identity, but it doesn't matter. It's identity. So then we get X transpose Y. So inner products are preserved. Inner product. So if you had two vectors in some space, and then you applied a vector with orthonormal columns, or more specifically, you can also go for an orthogonal matrix. If K equals N, you apply to them, inner products are preserved. So if inner products are preserved, then also the angle, which we don't need to think about specifically, between the two vectors, between the two images of this linear transformation is the same of the angle of the two vectors. And also, then you can do that, you'll just do AX transposed, AX transposed, okay? So, and this is nothing, sorry, not AX transposed, AX transposed times AX. This is nothing but the norm of AX squared, okay? And this, by the same argument, is going to be X transposed X, which is the norm of X squared. And norms are non-negative, so that means that the norm of A of X is the norm of X. Okay, that's this. That's these properties. All right. Any questions? All right, so let's take our 10-minute break, and I'll be back in 5 minutes, and then we'll continue in 10 minutes. All right, see ya. All right. If there are any questions, I'm back. Okay, so there's a great question. What's the application of the orthonormal matrix? So soon there are multiple answers for this. So soon we'll see that, first of all, representing a matrix, we can represent a matrix as an orthonormal matrix times an upper triangular matrix. And that's a factorization, just like we had the LU factorization. This is a different one. And that actually allows us to do many things, to solve systems of equations, but also least squares and other things. Now, also in numerical linear algebra, we often want to represent things in terms of an orthonormal matrix because we know that our vectors won't be too large, too small, etc. And algorithms that we carry on the vectors will be numerically stable. Numerically stable means that numbers won't go to infinity and then you'll run out of precision or won't vanish in the same way. But we'll see this today already. Okay. Any more questions, thoughts? So for those of you that are still not in Australia, first of all, hope to see you in Australia. And when the things are possible, here's a photo from the weekend. Has anybody seen a kangaroo in the past couple of days? I mean, they appear, not everywhere, but kangaroo. They exist. They exist. Does any non-Australian know the name of the child of the kangaroo, the baby of the kangaroo? Kangaroo, the baby of the the baby kangaroo. That's good. Yes, it's a joey. The joey. That's the name of the baby of the kangaroo, the child. Yeah, and so we could also I've seen this weekend for the first time. I've never seen that before. I've seen before the joey inside the mom, which is nice, kind of with the pouch with the head outside. But I've never seen before a joey outside and then jump into the pouch, and that was very cute. So we're driving by, and he was jumping into the pouch. You don't have so many in Brisbane just like that. You need to kind of get out. I'm just entertaining you with wildlife because you don't have linear algebra questions in the break, but maybe you have some linear algebra questions. Also from the weekend. This is a python. Python. They're not venomous. So I tried to touch its tail actually, but they're very hungry now. So they jump. Don't try. I didn't say, but we went to Girrawin National Park. Do you know it? Girrawin National Park. So Girrawin National Park. I'm afraid to misspell it, but Am I sharing screen? Yeah. So Girraway National Park, nice. So, and now we don't have full lockdown here. So this is I recommend Girraway National Park. 200 kilometers from here. For those of you in Brisbane and that can go, I recommend. Anyway, that's it. Okay, enough. We're not here in a nature course. We came to do linear algebra, which is actually very natural. It's a natural part of mathematics, and I think it also exists on other planets. And funny enough, the kookaburras are yelling outside. Let me just close the 6 in the evening, so all the birds have to say their final say. Okay, so next hour, next 50 minutes. So QR factorization, remember the LU factorization? QR factorization, another one. We take a matrix, and the long story short is we're going to represent the matrix as, so we take a matrix A, we'll represent it as A equals Q times R. That's what's called QR. Q is going to be a matrix with orthonormal columns, which if A is square full rank, then Q will just be an orthogonal matrix, and R will be an upper triangular matrix. Okay, so that's the QR factorization. Now, if you remember the LU factorization, what it does, it encodes the steps of the Gaussian elimination. And remember, LU was kind of an, you have PA equals LU because maybe there were some row swaps, and we never really got into that fully. That's the LU. Guess which algorithm QR describes? It's a Gram-Schmidt. Okay, so Gram-Schmidt, in a sense, what we're doing in Gram-Schmidt, let me move back here a second. And all the time, we're just discovering these new vectors Q. We're discovering these new vectors Q, and we're representing them as linear combinations of the previous V's. Okay. Gram-Schmidt algorithm, by the way, you don't even have to know all the V's ahead of time. They can be coming to you little by little, and you kind of compute the Q's online. Okay. I mean, if you're speaking with very high dimensional data or something like that. Okay. Now, with the QR, we're going to keep these relationships in A equals QR. And these are the equations. So look, the key equation in Gram-Schmidt was this. Qi tilde was Vi minus all the I minus one other vectors of the previous Qs. Okay, that was Qi tilde. And when we divide it, if this thing I'm highlighting now, if we divide this Qi tilde by its norm, we get Qi. So you could just say that Qi times the norm of Qi tilde is this right-hand side. So now let's kind of go the opposite. Let's just go the opposite. Let's take this V and put it on one side of the equation. So basically bring all these negatives here to the other side. So you see, Vi is Q1 transpose Vi times Q1 plus up to Qi minus 1 transpose Vi plus this last thing. Okay, so that would be Vi. Okay. So what we see is kind of nice. We see that Vi is a linear combination of Q1 up to Qi. You see, Vi is a linear combination of Q1 up to Qi. Okay, that's what you see with Vi here. Vi is a linear combination of Q1, Q2, Qi minus 1 up to Qi. Okay, so the weights of the linear combination are going to be, I have a bit of a typo here, are the weights of the linear combination, let's call R1I, we'll call it Q1 transpose times Vi, Q2 transpose times Vi up to RII. Okay, and what are those R's? This is not so critical, by the way, you just need to understand the concept. Okay, so the full details here are are basically we're reverse engineering from Gram-Schmidt to get the QR factorization. So then the Rij is going to be the inner product of Qi and Vj. And the Rii, the diagonal, is going to be this guy, Qi tilde norm. And Rij is going to be 0 if I is greater than j. Okay, because you see the Vi only depends on the first Qi. Okay, the Vi only depends on the first Qi. So when you put all these things together, what you get is the matrix Q here and the matrix R. Okay, where R is a matrix with Rij equals 0 for I greater than j, so R is upper triangle. Let me actually just write this in the notepad. So everything kind of makes just a bit more sense. I'll share the notepad again. All right. So what I want to do is we have a matrix A, and let's just think of the A in this case as V1. I'll just make it like this, V2, V3. Okay, that was our matrix A. Okay, so before I said, you know, collection of vectors, but now let's actually take the matrix A. Okay, and using Gram-Schmidt, we actually got these other vectors. We got Q1, Q2, Q3, so let's put them in the matrix Q. Okay, Q1, Q2, Q3. Okay. And what I want to say now is that A equals QR. Okay. A equals QR. So to do that, let me actually write V1, V2, V3 equals Q1, Q2, Q3. And now, just to be explicit, I'll actually write the matrix. I'll call it R11, R22, R33, R12, R13, R23, 0, 0. Oh, come on, Yoni. 0, 0, 0. Guy here, upper triangle. That's our R. Guy here, orthogonal. That's our Q. So, you know matrix multiplication. So this vector here, this V1, is the Q1 is, you can take this column here and do a combination of Q1, Q2, Q3. That's one way of thinking of the matrix multiplication. But 0 goes for Q2, 0 goes for Q3. So V1 is just R11 times Q1. And the R's are nothing but the norms of the Qi tilde. Okay, are the things that unnormalize it. It's the unnormalizer, the R. Okay, so that's how you get V1. That's how you can reconstruct V1. Okay, let's undo all this greeny stuff. We get to the next vector. V2. V2 is going to be, we don't want this green vector. Erase, erase, erase. Oh, live stuff. Let's not wait. Okay, so V2 is going to be, this V2 is going to be, this is going to be a linear combination of R12 times Q11 and R22 times Q2. Okay, and that's how you're going to get V2. So V1 just depended on Q1, or when I say dependent, not in a linear dependent sense, but V1 was only constructed by Q1. V2 is going to be constructed by Q1 and Q2. V3 is going to be constructed by Q1, Q2, Q3. Okay, it's a linear combination of all three. You see? So this is a QR decomposition. Okay, and the Gram-Schmidt algorithm basically creates a QR decomposition. We're not going to code that. We're not going to code that in the same way that Gaussian elimination creates the LU decomposition. Okay. All right. Let's go back to this sharing. Okay. Any questions? All right. So let's see the QR decomposition, and for this we'll actually use the linear algebra package. So here I have a matrix of 4 vectors. It has 3 vectors, but they're 4 dash vectors. So vectors of length 4, 3 of them. Okay. So and I'm just going to call the function QR. Do the help on the function QR. Okay. From the package linear algebra, and QR, it's going to, and you can do a few options, etc., but it's going to do the QR factorization. Okay. Now, the thing that it's going to do, it's going to do a slightly different QR factorization or decomposition than the one that we exactly showed. So I'll explain in a second. So you see here, the rank of the matrix A is 3. So that's good. I mean, these columns are linearly independent. That's what we learned, right? But still, we're not going to get a square matrix Q when we do Gram-Schmidt, right? Because what we're going to get is just a matrix Q with 3 vectors. So imagine if, in addition to A, we would also append an identity matrix to the right of it. Okay, so we'd also append here to the right all of the columns of the identity matrix. In this case, the rank of A would always be 4. Okay, so let me actually just show you what I mean. So if this is a matrix A, okay, let's try and do this. So I can always do A appended I. I'm not sure this will work. Let's see. Yeah, that worked. You see, that's A appended I. The rank of this matrix is always going to be 4. Okay, so let me actually do A append I, and on a different line, I'll do the rank of A append I. I'm quite impressed by Julia that it knows the I, it knows what dimension of identity matrix to do that, right? Because I is just like the unit scaling operator. So you see, because it's clear now that the null space of the vector of the matrix AI is 0, because sorry, that's not what I mean. It's clear that the rank is 4 because the column space of AI is all of R4. The column space of AI is all of R4. Because if you want to give me a vector in R4, you give me a vector in R4, and you ask, how do I represent this vector as a linear combination of these columns? Well, one way is you just ignore these other guys, these A bits. The I already does the job. Okay, that's one way to think of it. All right, so when we ask Julie, you can always do Gram-Schmidt on this guy, right? Now, if you would do Gram-Schmidt on this guy, but by some point, like if we were, let's actually, you know what? Let's be brave, and let's actually do Gram-Schmidt, the one we did, my Gram-Schmidt, which is maybe your Gram-Schmidt at this point. Okay, so let's do R. Let's call it R Gram-Schmidt. Okay, so let's do my Gram-Schmidt on AI. Now, okay, the Gram-Schmidt does. So if I take the AI, how do I get the columns of AI? So let's do it like that. There's probably better ways, but I'll take the matrix AI, and I'll take the ith column for I in 1, 2 size of, oh, come on, let's just call this AIB. Okay, yeah. Okay, let's call this AIB, and let's take the ith column of B for I in 1, 2 size B2. Okay, this should be the columns of B. There would have been a better way to do this. This is BI, invalid iteration specification. Come on. This is annoying. Size B2 is just 3 plus 7, it's just 7. Okay. Come on. 4. Thank you. All right. Thank you. Good job. Thanks. All right. So these are now the columns of B. Okay. These are the columns of B, right? And they're each an array. Okay. So now let's do my Gram-Schmidt on this guy. What is my Gram-Schmidt going to do? In this, what's going to happen in my Gram-Schmidt? Which there's some red stuff in Gram-Schmidt. What's Gram-Schmidt going to do? Gram-Schmidt's going to take the vectors, too many of them. It's going to quit, right? Gram-Schmidt will be a quitter. Let's hope. Let's see. It said linearly dependent. It even threw an error as though this is we're now the police, right? That error is from us, linearly dependent. It didn't have to be, by the way. You shouldn't have to throw an error. If you really want to be kind of a Julia programmer or program in general, you can throw an exception. Okay, so if any of you are interested, you can do mechanisms for throw an exception, and it won't just be an error, because this error is maybe like a bug as opposed to, say, an exception. But anyway, just like you said, it's going to quit because these are linearly dependent. Now, we could have had a Gram-Schmidt that does the following. It says, if I and maybe you'll have this in the second homework, but I doubt it because we've got a whole bunch of other things to have in the second homework. So you would say, if linearly dependent, then just ignore this vector, okay? And move and pull another one, like move to the next one, right? Now, why am I telling you all this? Because the QR factorization that you have in Julia, and that's in general when you have numerical software. So now I'm going to do F equals QR on A. I'm not on the matrix B, I'm in the matrix A. And the matrix A, just so you see here, the matrix A was a matrix which is 4 by 3. So QR returned to me this object, and it has a Q factor and an R factor. Okay, and I can do, by the way, at this point, I can do like F dot Q and I'll get the Q matrix, okay? And I can do F dot R and I'll get the R matrix. You see upper triangle. But look, the Q matrix is not 4 by 3. The Q matrix is 4 by 4. Okay, it's 4 by 4 because it did the complete QR factorization. It also appended an identity matrix to this guy. Okay, that's what QR did. So if I want the QR that I just taught you about that does not append this, what I'm going to do is I'm going to call the matrix Q is going to be F dot Q, just the first 3 columns, because that fourth column came from the appended identity matrix. So that's going to be the Q matrix, and that's going to be the R matrix. Okay, that's a Q matrix. And the R matrix is just what it was. And then look, if I do Q times R, I indeed get the reconstruct the matrix. So far what you've seen Gram-Schmidt, you've seen how to do QR, and sorry, there was a question I ignored. Why should we do QR decomposition? So I'll show you in a minute or two. Okay, so the strength of the QR decomposition, and it'll appear more and more and more in least squares, which we'll get to as the evening or afternoon for those in different time zones progresses. Okay, so now you can also get what I'm going to do here, if I do copy here, I'll get the full Q. The reason I'm doing that is that when you do QR decomposition, look, F dot Q, the type in Julia, it remembers it's of a special type, and then some things it doesn't just treat it as a matrix. Okay, so this changed the type of it just to a matrix, an array of floats. But don't worry about it. That's a full Q. So look, if I do full Q transposed, that's just like the inverse of this full Q, right? So Q is an orthogonal matrix. Okay. So that was QR decomposition. And here now, look, I have an A, which is no longer full rank, okay? So I've taken the A of before, but now I've appended, look at this third column. So the third column is just the sum of the first two columns. You see, this third column is the sum of the first two columns. You see, it's 3 plus 2 is 5, etc., etc. The fourth column is new. So the rank of this A is again 3. I could still do a QR decomposition, but now what I get on the R, look on the R matrix, is I get something here, which is fine. I get something here, which is fine, but then I get a 0. That 0 in the R matrix indicates to me that this third column is a linear combination of the previous columns. Okay, that's how I got the 0. That's all I want to show you there. Okay, so now let's see some first use of QR. Okay, and if you are reading, as you should be a bit here and there, the VMLS book, this guy, okay, then you won't find Gaussian elimination. I think one of the premises of this book is to do quite a lot without Gaussian elimination. Okay, but you still solve system of equations. And if you go to section 11.3, you'll see how to do it using QR. And that's, by the way, how actual solvers often do it. They do the QR in a better way than what we did the Gram-Schmidt. And when I say better way, again, you need to do numerically things better because you want numerical stability. So there's some different ways of doing it. Because you can order the vectors that you put into Gram-Schmidt in a different order, and you'll still get a QR factorization, right? So if I give you a collection of vectors, remember Gram-Schmidt worked on a collection of vectors, you don't have to take them in the order that I give you. You might choose a different order. And sometimes you get better numerical performance. The other things that you would do that kind of professional software would give you more, less cache misses. So we'll work on memory locality. And that's why, we're just doing this to kind of understand how things work from a linear algebra perspective. This is not a course in numerical linear algebra. All right, so if you want to solve AX equals B, okay? So here's a way to do it. You say A equals QR, and now let's assume that A is square and full rank, okay? Let's just assume that A is square and full rank, meaning it has a null space of 0, meaning there's a unique solution to AX equals B, okay? So let's assume we can solve AX equals AB. We want to solve it. Instead of doing Gaussian elimination or an LU decomposition, what you'll do is you'll describe A as QR. So then what you have is QRX equals B. So now you see this QRX equals B, and it's just, you kind of like it because Q is an orthogonal matrix. What's the inverse of an orthogonal matrix? What's the inverse of an orthogonal matrix? The inverse of an orthogonal matrix, Q transpose. Q transpose is the inverse of an orthogonal matrix. So instead of multiplying by Q inverse, which is a complicated, expensive operation, multiply by Q transpose. So then you have Rx equals Q transpose B. And now solve. But why do I like to solve Rx equals Q transpose B more than solving AX equals B? Why is this painful? Why is this highlighted thing painful, but this less painful? Why is this less painful? This we actually implemented. When R is upper triangular, remember we implemented it ourselves. Backward substitution, easy peasy. And not just easy to implement, easy to run. It takes n squared operations as opposed to n cubed operations, in order of n squared operations as opposed to an n cubed, because backward substitution, you're summing up the arithmetic series here, which is n squared. I mean, that's when you count how many operations are needed. Okay. So then you would solve this, okay, using backward substitution. So all you need is backward substitution. You do not need Gaussian elimination. So you need Gram-Schmidt to do the QR, and you need backward substitution. You can solve a system of equations. Now, here's a little demo just so you see that this is fast. But just to be clear, to be fair, this is not faster than doing an LU decomposition, which is Gaussian elimination. Okay, but once you have the factorization, it's fast. And if you remember, just like with an LU decomposition, you know, you can do the factorization of the matrix once, and you can solve for many right-hand sides B, right? The same with the QR decomposition. You can do the decomposition once, and you can solve for many right-hand sides B. Okay. The complexity of QR decomposition is similar to LU decomposition, so we haven't gained there. Okay, but it's an alternative view. So what I have here is a little demo here. I'm setting the seed. This is just so this gets the same numbers every time. And let's take n to be 6,000. Okay, so let's have a 6,000 by 6,000 random matrix, and B to be the random right-hand side. And let's do a QR decomposition of this matrix A. Okay, let's run this. This will take a bit. This is going to take a bit. But this is operation, this QR decomposition, this is like, let's say you do it once. Okay, so once you do a QR decomposition of the matrix A, and then we're going to apply a whole bunch of right-hand sides to it once you have it decomposed. So this thing is still running. Let it run for a bit. 6,000 by 6,000 is a big matrix. Okay, it took some time. All right, let's just see that by the way, that this is, you know, if you do Q transpose Q, it's a big matrix. Okay, it's still a big matrix multiplication because it's multiplying. It's 6,000 by 6,000 matrix. Just the memory allocations it's doing are kind of big. Okay, maybe I shouldn't have done that actually. But this is going to give us an identity matrix, but like a 6,000 by 6,000 identity matrix. Okay, so that's, if I'm not mistaken, we have 36 million entries in this matrix. Maybe I should stop it. We believe you, it's identity matrix. Okay, but now look. What I'm going to do is I'm going to time the operation just of A backslash B. So this is without prior QR or LU or any decomposition. Okay. So, and what I'm going to do here is I'm going to do the norm of AX minus B. Okay. So we want that norm to be almost 0 because AX should equal B. Okay, so we'll time how long this takes. And this took 11 seconds, and you see the norm is 0, right? So X is indeed the solution to AX equals B. But here, let's do Rx equals Q transpose B. Okay, so this is Rx equals Q transpose B. Solving for X. But I'm actually telling Julia, I'm telling, hey, Julia, the matrix R, just so you know, it's upper triangular. So the smart backslash operator knows that if you take an upper triangular matrix, you don't need to do Gaussian elimination. You can just run back substitution. Okay? So remember, QR factorization has already been done for us. Time this, 0.6 seconds. Okay? And you get a solution, which again is the norm of AX equals B. Yeah, so you see, now you can do the same exercise, by the way, with LU. Once you factor a matrix to LU, then you can solve this. But remember, with LU, you'll need to do 2 back substitutions, remember? So if you review how we did it with LU, you need 2 back substitutions. So that was one use of QR, but the real important thing will be when we get to least squares. Which is soon. Any more questions? So by not doing upper triangular, first of all, let's experiment a second. Let's actually just copy this and so by not decorating the matrix R as upper triangular, oh, it actually, maybe it knows by itself somehow. So let's see what the type of R. I'm surprised. Okay, so now I'm surprised. So there was a question, why do I need to run upper triangular? So I thought when I did this that this guy won't be smart enough to know that R is upper triangular, and then I'll do back substitution. But I guess I didn't even need to run it to decorate as upper triangular. So that means that this backslash operator goes to the matrix R and somehow checks that it's upper triangular. Right? If you decorate R as upper triangular, its type, when I say decorate, its type is upper triangular, and actually it just stores in memory just upper triangular. See, it stores nothing for the lower triangle. But I guess I didn't. Okay, more questions? Okay, but you see, okay. Yeah. All right. Next big story, which is related, is projections, and that brings us on to least squares. So let me share the scratch pad for this. And let me tell you this story. Okay. So the story is that we have some vector. We're here in the Cartesian plane, and we have some vector u. Okay, so this is the point u. So let's treat the vector u in this case as this vector, but let's actually think of it as this whole subspace spanned by that single vector u. Okay, so in this, I'll think I'm drawing an arrow for this u. Okay, that's a vector u. Okay, sorry, let me call this vector, if you don't mind, v. Okay, this is a vector v. Okay, and now I'm given another vector. Let's draw it here in red. No, let's not draw it in red. Let's draw it in blue. And this one, and that's going to be the vector u. Okay, that's going to be the vector u. So what we want to do is say our life is just on this line associated with the vector v, and we now want to find some point on this vector v, or we want to find some point on this line spanned by the vector v that is closest to the vector u. So which point is closest to the vector u is the point A, the point B, or the point C. Which point is closest in the span of v to the vector u from A, B, or C? It's B, okay, as you see. B is the closest point, okay, vector B. All right, so what we're gonna do is we now wanna describe this point. And this is called projecting, to project like a projector. You see what a projector does, it projects on a screen. To projecting, like we don't have projectors anymore because we're COVID-19, so we don't project anything anymore. We're just in our rooms teaching each other, but no, you guys go to the practical, so you see some projections. Okay, so we're going to project the vector u onto the vector v. So we want to find this point which is closest. Now, the way to find this point is, what we'll do is we'll say, let's assume that we have this point. Okay, and let's call this point P. Okay, P for projection. Let me actually do it in green, just to be a bit consistent with what's to come. Okay, so that's a point P. Okay, we want to describe this point. So first of all, since P is spanned by the vector v, we know that P is some x hat times v, and that's a scalar. Okay, so P is some multiple of v. Okay, but we want to find this P. So one way to do this is to look at this thing here, which is the error. Call this the error, because if this error was just zero, was just a zero vector, this is now, I'm drawing a vector as like a line, okay? This error here, if it was just a zero vector, then we know that we have like u is actually in the span of v, okay? But otherwise it's not, but still we have some error here, okay? And this error is going to be u minus p. Okay, it's a vector u minus a vector p. Now I draw the arrow like this. Of course, if you draw u minus p, what you're getting is something here, right? That's u minus p. But now consider it as drawn. That's it. So what do we expect the inner product of u minus p and v to be? What's going to be the inner product of u minus p and v? What's going to be the inner product between this error and v? What's going to be this thing? 0, 0, because the angle is going to be 90 degrees. Okay, so we want E to be orthogonal to V. Okay, so if this inner product is 0, okay, now let's just do a bit of algebra. So let's do U transposed V minus P transposed V. Okay. Am I doing the right thing? Yes. But instead of P, let's write X hat V. Okay. Instead of P, we have X hat V. And instead of P transposed. Okay. So let me just switch to black here. So then we have U transpose V minus X hat V transpose V, and I'll do this because X hat is a scalar in this case, and that needs to be this equals 0 and this equals 0. Okay. So now let's solve for X hat. Let's solve for X hat. Whoops. Let's solve for X hat. Okay. Let's solve for X hat. So then we can say that U transpose V equals X hat times V transpose V. This is a scalar. This is also a scalar in this case. Or X hat, if you'd like, is U transpose V divided by V transpose V. You can also write that as U transpose V times the norm of V squared, if you'd like. Okay. So that's our X hat. So the projection then is U transpose V divided by V transpose V times V. Okay. This thing I'm highlighting now, that's again our X hat. Okay. So projections basically take the inner product and then normalize by V. Okay, and that's going to be this point. Okay. So that's how we project onto a line. This is the projection principle onto a line. All right. Questions about this? All right, so let me stop this. Let's see it a bit in the notebook. So here we have V, that is, we're just in R2 in this case. So V is 10, 10, okay. We want to project, we're going to project onto V, okay. And U is a 0.24. So X hat is the inner product of V and U divided by the norm squared. So the projection is X hat times V. And the error is U minus P. Okay. And if I run this, oh, I guess I'm running this, so now plot is going to take a first time to plot. So I'm going to plot a few things. So the thing is, when you're plotting, I actually want you to see the plotting. First of all, to make this look nice, the aspect ratio should be 1. So that just means that it's drawn on the screen exactly on scale. So there's no stretching on X and Y. We don't want a legend in this case. We're using 4 different colors: yellow, blue, green, and red. Line width is going to be 5, fine. But here, this is important. This is the X coordinates, and these are the Y coordinates. So this plots the vector V. Okay, so this plots the vector V. This plots the vector U. Okay, this is vector being projected. This is vector projected onto. Okay, there's a question. The exclamation mark in the plot, there was a question about exclamation mark in the plot, it adds to the previous plot. Okay, so you do plot and then you kind of draw on it, plot more, plot more, plot more, plot more. Okay, it's like using that notation of changing stuff. Okay, so this is a vector v, this is a vector u. Okay, so the vector v is in yellow, that's a vector v. Okay, that's a vector 10, 10. Okay, the vector u is the vector in blue, that's a vector 2, 4. You see 2, 4. Okay, this is the vector p, the actual projection. Okay, and that's this green line. Okay, so p is x hat times v. Okay, and here this is the error. So the error has first coordinate p1, and the coordinate here is p1 plus e1. Okay, that's p1 plus e1, and p2, and then p2 plus e2, and that's it. Okay, that's projection onto a line. Of course, you could have changed the. So just a question: if say I change this like this, u equals 2, 2. What's x hat? What's x hat going to be? Or maybe it's not so easy actually. Okay, let's start with this. What's x hat going to be here? What's x hat going to be here? 1. Okay. All right. And if I'm at 1, 1, what's x hat going to be? Yeah, 1. I agree. Okay. Is it 1? I'm not sure. I don't think so. I don't think it's going to be 1. I think x hat needs to multiply v to get u. What are you going to multiply by v to get u? 1/10, right? So in this case, u is already in the span of the vector v, fine, but we still need to do the stretching, right? Because the vector v, you could have described this subspace, this yellow subspace, using this vector v. Of course, you could have used this vector v as well, right? So let's put it here back in something like this. You know, this is a different vector v to 2020. And that's a different vector. About this square 9 square 9 square, no, I don't think so. So I think if this is 10, and if this is 1 and 1, then x hat, so now you see u is already on the subspace spanned by the vector v, but x hat is 0 point like this. Okay. All right. So that is how you project a vector onto a line. Okay. Now the story can continue, and we can project a vector onto a subspace, and that becomes quite a powerful story. Okay, projecting a vector onto a subspace. Right. So let's first of all motivate this. Okay. Let's motivate this, and this thing is a big deal. Is a big deal. So we want to solve ax equals b. We want to solve ax equals b. Okay. What does it mean when we want to solve ax equals b? We want a linear combination of the columns of A such that that linear combination gives us b. Okay. Now, ax equals b will have a solution exactly in the situations where b is in the column space of A. Okay, if b is not in the vector space, which is a column space of A, then we won't have a solution, right? Then we won't have a solution. Okay, just to make this concrete, let's already create an example. Let's take A to be 1, 2, 3, 4. 5, 6. Okay. The column space of A, what is the dimension of the column space of A? What is the dimension of the column space of A? Just to, if you want to make sure this, let me also see rank A. Okay. So it's not that I by accident picked the second column to be a linear combination, to be a multiple of the first. Okay. So what is the dimension of the column space of A? It's 2, right? So even, and it's a subspace of R3. Okay, the column space of A is a subspace of R3. We've already seen this, right? Any linear combination with columns will work. Okay, now if I take a B, for example, which is, let me actually pick a nice one. I'm going to take B to be 3, 7, 11. Okay, 3, 7, 11. Okay, what I did is I added up the columns. Okay, I added up the columns. So this A solution to AX equals B is A times 1, 1. 3, 7, 11. Okay. In this case, I can solve AX equals B exactly, right? But what if I choose some other B? You know, I'll just choose something 2, 4, 19, for example. Okay. Now, I'm kind of taking a bit of a chance here, but the odds are with me. Do you think 2, 4, 19 is spanned by the columns of A? Just if you want to kind of take a wild guess. And I pick some random numbers, some kind of arbitrary numbers, I should say. Is 2, 4, 19 spanned by the columns of A? No, probably not. Probably not, right? But I still want to solve AX equals B. So what I'm going to do is I'm going to take the column space of A, and I'm going to find the vector that is projected by B onto the column space of A. Okay, I want the best projection onto the column space of A. Okay, that is kind of the name of the story, and that's what we're going to do. Okay. So what we're looking is for some vector P, which is in a sense closest to this B that we want. Okay, so let's draw a story. Let's draw an illustration for that. We've got 3 minutes, so we could start it, and then we'll take a break. So just so we see this, so I'll make it kind of concrete, so to relate with the numbers that we just drew in the notebook. So we have A, just to be concrete, 1, 2, 3, 4, 5, 6. Okay, so now I'm a bad illustrator, but what I'm going to draw is this plane. So think of this plane as like in R3. Okay, so you've got here, you know, your X and your Y and your Z, say, you know, or let's call them the X1 and the X2 and the X3 is like the 3 coordinates. And this here is some plane that lives, and that plane, you know, of course that plane it's a hyperplane that intersects the origin, because that plane is it's the span of the columns of A. Okay, that's what it is. Okay, I'm writing here in formula. It's all the linear combinations of this vector and this vector, and they lie on this plane. Okay. Now we have some other vector B, and we'll draw the vector B. Let's be consistent with before, with like this blue vector. Okay, so we'll draw this vector B here. It's going to be this vector B. Okay. We would have liked, it would have been great if B would actually be lying on this plane, because then we know that AX equals B has a solution, A equals B. But life is not so good to us. Well, it is good to us because we're data scientists and we're going to make our living from this projection. So, you know, maybe it's good. Okay, so we're going to look for some point here, which is the projection of B. Now again, I know this is trivial, but just like last time, if I could put these 3 points, here's a point call it capital, let's call it X, and this point, let's call it big Y, and let's this Z, this point big W. So from the points X, Y, Z of W, which point would you want to choose as the projection? W, okay? So you want the point that is orthogonal to the vector B and minimizes this error, okay? So you basically, and you also see that if you deviate from this point, then the error kind of wherever you go, in each of these points, the error is bigger. So what we'll want is we'll want the error here to be orthogonal to W. Just like when we project it onto a line, what we're doing is we're just generalizing. We want the error here to be orthogonal to this point P. And that point we'll call it P. And that's going to be the projection point. So we'll continue this just after the break. Okay. So I'll again appear in 5 minutes. And E is in the null space. Yes, it is. Well done. Any questions? So we'll get to the null space of A transpose and the null space. So no questions. So is anybody here doing the stats course in parallel? The probability and statistics bridging course? Oh, you're doing both. You've got two probability generating functions already? Or not yet? They took it out. Okay, really? That's interesting. Oh, at least for the midterm. Okay. But you've got random variables, binomial distribution. That's the best one. Geometric, mean variance, expectation. It's the best. No questions? So there's a question, an n by k equals qr in here. N should be greater or equal than k. No, you will still get a QR factorization, but R is not going to be directly upper triangular. Okay, so you can get a QR factorization for any matrix, but then R will be, whenever R discovers, whenever Gram-Schmidt discovers a vector that is a linear combination of the previous ones, you're going to get a 0 in R. So R is going to have this kind of jagged form of, it's not going to be directly upper triangular. Okay, so that's what's going to happen. Okay, you can try it. We might try it if we have time. So for an arbitrary matrix. Okay, Dash, you want to say hello now? Come on. No, he doesn't. Okay, let's not get him worked up. Any more questions? Open for dog. Be right back. Okay. 7 p.m. in Brisbane, and we're continuing with our projection onto a subspace. So again, I'll just draw it nicer. No, let's just stay here. So no, let's just draw this thing again. So we've got here, this is the row space of A, okay? Sorry, the column space of A, the range of A. I confused row space, it's a column space of A. Okay, so that's what's spanned by A. And we've got here the vector B. And we can't find a linear combination of, or B is not in the column space of A. Okay. So what we want to do is we want to find this point here. Okay. We want to find this point here, and we'll call this point P. That's going to be the projection of B onto A. Okay. It's going to be the projection of B onto A. So the way to describe this point is we want this point to be, or we now want we can look at the error again. We can look at the error, and let's call the error, B, this error here, let me draw it in red. The error is a vector. It's B minus AX hat. Okay, so this point P here, the projection point P, is going to be AX hat. Okay, so we're going to find some linear combination X hat. Before X hat was a scalar. Now we're going to find some linear combination of the columns of A. So we're going to get AX hat, and that's P. And P is in the column space of A. Okay. So we want B minus X hat to be, we want this, we want now the error, B minus X hat, B minus AX hat, we want that to be orthogonal to anything that's spanned by the columns of A. So what we can do is we can write this is we want A1 transpose. So now if we treat A as now call this A1 transposed. So let me write a bit nicer. So we've got the first row of A is called that A1 transpose. That's the name we're calling the rows. The second row is A2 transposed up to the last one, which is AN transposed. Okay. Sorry, I'm making a mistake. Hi, sweetie. I'm still teaching. So. Okay. So, sorry. A is M by N, and we've got this column A1, this column A2, up to this column AN. Okay. Now we can treat A transposed. We'll now write A transposed. That's going to be A1 transposed, A2 transposed, up to AN transposed. And A transposed is an N by N matrix. Okay. So we want anything that's spanned. So you want anything that's spanned by these columns, okay, to be orthogonal to this error. Now, what's anything that's spanned? Anything that's spanned is any linear combination of these columns. So specifically, it's enough to, so this is a vector, that's a vector space. So specifically, it's enough to take this column, you'd want it to be orthogonal to this. And this column, you'd want it to be orthogonal to this. And up to the nth column, you'd want it to be orthogonal to this, because these columns, their span defines this space. So basically, the equations you have are like this. You want A1 transpose times this guy is E, this guy is E. You'd want that to be 0. This is a 0 scalar. And A2 transpose times this, you'd want it to be 0. Up to AN transposed times the error. Each time I'm taking here the same error. The error is, let me paint the error red. Oh, that's the error, that's the same error, that's the same error. We'll want all of them to be 0. So I can represent all of these things as all these equations. I could just represent it as A transpose times B minus AX hat should be now this, all these zeros should be the 0 vector. Okay. So I'm going, this is the orthogonality principle for projecting B onto the column space of the matrix A. So now there was some things in the chat that says there's something was said in the chat, should A be in the null space, and somebody corrected, and that's very good. We're looking for the error E here in the null space of A transposed. The error E is in the null space of A transposed. Okay, that's what defines the error. Now, once we have this, so this equation, which we have here, oh no, this equation which we have here, we obtain via the orthogonality principle. So just through requiring, I mean, it's quite a complicated thing. It was simple for the line. Here you need to just think a bit more. You'd want each one of the basis vectors of this subspace, each one of them, the A1, the A2, up to the AN, you'd want each one of them to be orthogonal to the error. And that means that everything in this vector space is orthogonal to the error. Okay, so this is a big thing. Okay. Once we have this, we can do a bit of algebra. We can do a bit of algebra. So let's now take A transposed B minus A transposed A x hat, okay, equals 0. Okay. Let's make this a bit nicer. So let's do A transposed A x hat equals A transposed B. Okay. So these are now equations that describe our x hat. Our x hat. Remember, our x hat here is the, once we multiply, our x hat says how to do a linear combinations of the columns of A to get this point P. Now, these equations, they have a name. They have a name. They're called the normal equations. Okay. This matrix, there's a name for this matrix. You've seen this, A transposed A. What do we call such a matrix, A transposed A? I drew it, I sketched a bit. My handwriting was so nice. A transposed A. What do you call the matrix A transposed A? It's a symmetric matrix that describes it. There's also like a name when you take a matrix A. It's the, starts with a G, the Gram matrix associated with the matrix A. Okay. Now, you've seen in the practical, Walla showed you in the practical, that the null space of A transposed A is the same as the null space of A. So now let's assume A has Li columns, linear independent columns, okay? So A is, I'm just saying it in a different way, skinny, full rank. Okay, let's assume that. okay? Or null space of A, null of A is 0, just a 0 vector. Okay, so if we assume this, and this is an assumption we'll make until towards the end of the course, so when we're doing these projections, we'll assume that we don't have in this system of equations that we're speaking about in this AX equals B that we're looking at, we don't have linearly independent columns in A. Okay, we don't have too many, we don't have a column that says nothing new. Okay, so if we have that, then A transposed A is non-singular. I can write that if you'd like. The determinant of A transposed A is not 0, or the inverse of A transposed A exists. Okay, so then I can take the normal equations and I can say, let's multiply by the inverse of this guy. Okay, and by the way, if A has its if and only if, so if A does not have linearly independent columns, meaning it's not full rank, then A transposed A is singular, and then I cannot do what I'm just about to do. Okay, so then I can multiply by the inverse of A transposed A, so I get X hat equals A transposed A inverse times A transposed B. This looks like quite a lot of notation. However, a big moment has just arrived in your data science career. I'm not joking. You have just seen the most important matrix in data science, and it's called a dagger. This thing, dagger, it's like a dagger. It's the Moore-Punroe pseudo-inverse. The Moore-Punroe pseudo-inverse. You'll see it a bit more in the notes. So that's a matrix A dagger. Okay. Now, it exists here when A has linearly, it exists in this form when A has linearly dependent columns, and then the Gram matrix associated with A is non-singular. This is a square matrix, so you can actually compute this inverse. Okay. And that's your A dagger. That's your A dagger. So you actually get a formula. This is a very powerful formula. Okay. This is a pseudo inverse. Okay, there's not a single pseudo inverse to a matrix A, there are multiple. This is a pseudo inverse. It's also a left inverse to the matrix A. We'll see this in a few minutes. Okay, so you get that X hat is A dagger times B. This is quite, I'm saying a lot of things, but this is kind of the heart of the course, really. And the course has several hearts, by the way. All right. This is one of the important hearts. All right. So then our P, our projection, so if X hat tells us how to do a linear combination of, that's the X hat, a linear combination of the columns of A to get the projection P. So the projection P is X hat, is A times X hat, which we can now write as A times A transposed A inverse A transposed B. Okay, so this thing I'm highlighting now, not as important as a pseudo inverse, but a friend of the pseudo inverse. It's A times the pseudo inverse. Okay, it's A times A dagger. This guy, let's call this the matrix P. That's a matrix P. What does P stand for? P, anybody? Was I on mute the whole time? Projection. Okay, P is a projection matrix. That's a projection matrix. Okay, that's a projection matrix. So the matrix P is this matrix that takes B, takes a point B, you apply P to the point B, and you get a point little p. This is a little p, this is a capital P, which is the projection. Okay, that's a matrix P. All right. Matrix P, which we can also, just for clarity, we'll write that's A times A dagger. Okay, and that was the A dagger, this was this guy. That's a Moore-Punroe pseudo-inverse. Okay. Let's look at some properties. Let's look at some properties of matrix P because they're fun. They're fun. Okay, let's look at some properties of the projection matrix. First of all, let's see what is P transposed. P transposed. I mean, this is just fun. This is just fun. You just take P transpose. So what do I do here? I do here A transpose transposed. So I took this to the leftmost side. Okay. And then on this matrix, let me do something like, let's try at least A transposed A. I'll do like a minus transposed. Okay. We'll do something with that in a second. This was like here, and this A, let's write an A transposed. So what's A transpose transposed? This guy here is just A. Okay. And this guy, we have a minus transpose and inverse. We can write a minus transpose because a matrix, any matrix B minus 1 transposed is B transposed minus 1. Okay, that's true for any matrix that has an inverse. We're talking about square matrices, obviously, because we're speaking about inverses. Okay, like that. Okay, so what we can do is we can take the transpose of this Gram matrix, but the Gram matrix you already told me is symmetric, so then you get just an A transposed A inverse, A transposed. So what did we just learn about the matrix P? A lot of notation on the board, and it's late, but what did we learn about the notation P? About the matrix P? It's a projection, yes. What did we learn? It's symmetric. Okay, so P is symmetric, okay? So P is symmetric. Okay, symmetric check. Now this one is even more fun. Let's do P squared. Let's do P squared. Let's do P squared. I love this. This is like, I mean, this you got to do by yourself later. You know, you just sit and you just do, and you should enjoy this. I mean, this is kind of as fun as things can be. A times A transposed times A times A transposed. By the way, in statistics, this is called the hat matrix, okay? You guys are going to do all kinds of stats later on. This is the projection matrix in linear regression. This is, by the way, in the heart of linear regression. If you didn't realize yet, this is going to be the heart of least squares, linear regressions, all this stuff, okay? So when we're doing P squared, this is like 1P, and let's do another P, okay? Let's do another P. We've got an A, this is an inverse. A transposed A inverse A transposed. Whew, a lot of things, but we can cancel like there's no tomorrow. Just, you see, for example, this cancels with this because that's the identity. And what did we end up with? What does all this equal? This was another P before. What is all of that? So what's P squared? It's P. It's P. And that kind of makes sense that P squared is P because you see the projection matrix took the vector B and projected it, splat, onto the subspace. Say you're going to project it again, it doesn't want to move. Okay? And you guys know already that project, and you see, by the way, that projection here is a linear operation, right? So projection is just a linear operation of the vector B, and that projects it on the subspace. Project twice, it doesn't matter. Project 70 times, of course, what's P to the power 129? It's, if P squared is P, every time we multiply by P, it's still P. Okay, capital P. All right, good job. All right, so that's projection. That's a projection matrix. That's a hat matrix, and we got that through this key thing. It's in a sense slightly involved in a 3-hour lecture, but we got it through the orthogonality principle. Okay. Are there any questions before I move on? Okay, so let me move back to the Julia. Here. All right. So here you have exactly what we just spoke about. And what you can see yourself when you review this, the case of projecting onto a line was nothing but the vector A, the vector that we projected onto. So we projected onto the vector V, it's just a matrix, okay? So if you take this formula here of projecting onto the line, you see, you can, this is a formula where in the line formula, the V transpose V, I could have written this. Let me actually copy this and just write it in a slightly different way. Okay, so I'll go here, and I'm putting this formula again. Okay, but instead of writing it like this, how about I write it like, I'll just write it like this times this to the -1. I mean, these two formulas we have above are equivalent, right? Now, I can divide here by V transpose V. V transpose V is a scalar. Okay, and so I can say it's like multiplying by the inverse of V transpose V. Okay, it's like multiplying by the inverse of V transpose V. But I could have written this also differently. I could have, instead of a I could have written it as U transpose V here. That's fine, right? I can change the inner product to symmetric. I could have written as U transpose V. And I could have also, if I'd like, taken this scalar and stuck it inside. So let me take the scalar here and stick it inside here. I'm allowed to do this because it's a scalar. Okay, it's a scalar. And the last thing I could have done is I could have written all of this multiplied by U. I think I'm confusing myself now. I'm maybe making a mistake, but I could have taken all of this U. So wait, we're projecting the vector U. So U is our B onto the vector V. Yeah. So oh no. So I take it all back. Let me actually. I won't do this. So V transposed, and I'll put here a U. Okay. I'll keep it like this. But okay, let me back up a sec and make this up. Let's just go. Okay, I'm here making a mistake, but let's just see this a second. So when we have we want to get to this formula, okay? But we want to see it just as a special. We want to see the formula of projecting onto a line as a special case of this. So let's just do this here. Let's do this here. So, and here again, we said we projected the vector U onto the vector V. So what do we mean by projecting the vector U onto the vector V? We mean that A is simply the vector V, right? So A, the matrix A, is just a column, single column. And we meant that B, which we had here, was a vector U. Basically, what we're trying to solve, if we're saying A x equals B, is like Vx equals u. Sorry, it's a bit stupid what I'm doing, but that's just the way the lecture has gone. But it's okay. We'll learn something from this, and maybe you learn from my hesitation. Okay, so Ax equal b is like Vx equals u. So now let's use our projection formula. So our projection matrix P should be this guy, A times A inverse of A transpose. Da, 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 da. So that's, if A is V, it's going to be V times V transposed V times V transposed times U. That's a projection matrix. Okay. Now in this case, this guy is a scalar. Yeah, and that's what we had. So V transpose V. Oh, this is my mistake. So oh, okay. So you see this, because everything is a scalar now, I can actually write the V transposed, oh, inverse, sorry, inverse. Because everything is a scalar, I can now work that and I can say, not a problem. That is like the fraction of this guy time divided by this guy times the vector V. Times the vector V. So, and that's what we had in the line, right? V transpose U divided by the inner product squared times the vector V. Let's go back to the line. So let me erase this thing. Yeah. Okay, V transpose U divided by that times V. Okay, you see? So the projection onto the line is, of course, a special case, but we started with it because it was simpler. Any questions about this? It's a lot. It's a lot, but now we'll see something to do with it. Okay. Now let's actually first just do an example. I started with an example, and let's continue with it. So we had our matrix A here, and we had the matrix B there. Okay, had the matrix A, had the matrix B. So before I actually speak about least squares, which is related, it's in a sense the same thing. Let's do this. So we have the matrix A, and we have the vector B. Okay. We want to project B onto the column space of A. So let's do this. Let's do our projection matrix. Is going to be A transposed. Was it A transposed? It's no, sorry, not A transpose. It's A times the inverse of A transpose A times A transpose. That's our projection matrix. Okay. Let's see that this satisfies the properties of a projection matrix. Is it symmetric? Yes. And what am I going to get if I'll get P times P, for example, which is like P squared? I'm still going to get P. Okay. Now, I can apply this projection matrix onto, like here, this is a projection matrix applied to B, and that's going to be the projection point. Projection applied to B. This is this point. Okay, that's this point. So let's call this point, that's the point little p. Okay, and this is in the column space of A. Let's see that this point is in the column space of A. What I'll do is I'll do A might divide it. I do backslash operator A divided by P. I hope I'm doing this correct. Yes. Okay, so and let's call this X hat, just X. So what I've solved here, I've given a system of 3 equations and 2 unknowns, right? Because A is 3 by 2 and B is 3 by 1. So this, I'm just saying solving 3 equations, 2 unknowns. Now this vector, which is effectively 1, this x, if I now do A times x, what I'm going to get is my point B. Okay, 3, 7, and 11. But this was a point. This specific B was already spanned by the columns of A. Okay, I think that's how we created this 3, 7, and 11. So that's it's spanned by those columns. However, let's now choose a different B. Let's choose a different B. So I'll just do B. I'll just call it B again. I'll choose something else. 2, 24, and 3. Okay, which is probably I'm using my luck so that it isn't in the call space of A. I could still now do the projection matrix applied to B. Okay, and this is our X. Okay, now this X, we hope, is spanned by the columns. We don't hope, we know it is. It's spanned by the columns of A. Just if you want to see this, let me do A divided by, sorry, let's not call this X. This is P. P is not the X. That's a projection. P is a projection and X is the, this. So A divided by P, or it's not divided, it's solved this linear equation AP. Let's call this guy X. Okay. So if you now apply A times X, you're going to get the point P. Okay. So that's a projection. Now, just another point that you should know, we had there the projection matrix P, which I think I'm throwing quite a lot of information on you, but it's just treat this as an exercise of what we've just done. The projection matrix is A times the inverse of the Gram matrix times A transpose, right? Now, we call this guy the pseudo-inverse, okay? So just to see that, let me copy this whole projection matrix down there. Okay, and let me write A DAG. That's a pseudo inverse. Okay, that's going to be the inverse of A transposed A times A transposed. So, and the pseudo inverse is not a square matrix. A projection matrix is a square matrix. Okay, because it takes, the projection matrix takes a vector from Rn and it puts it in Rn. That's what makes it a square matrix. Okay. But the pseudo-inverse is not. The pseudo-inverse is, it has a different dimension. Okay, because the pseudo-inverse is the dimension of A transposed in this case. Okay. And of course, A times A DAG is going to be the projection matrix again. All right. Now, one last thing on this, you can also use a function, the built-in function pinv, which stands for pseudo-inverse, and you do pinv of A, and what you're going to get is again the pseudo-inverse. Okay, so that's projection matrix and pseudo-inverse. I have a bit of a problem here for 1 second, so I'll be just back in a quiet set. 1 sec, just call me if you need that. Take that out and now. Dash out. Sorry, my dog was walking around just as though there's an accident about to happen. It's sorted out. So, any questions about this? A lot of stuff you've had. You've got pseudo-inverse, you've got projection matrix. Okay. So the next bit of the story is actually going to look at the whole story of a pseudo-inverse in a projection matrix. It's heavy, I know. but it's repetitive. It's basically a few things. You've got projection matrix, pseudo-inverse, a bit of these, the fact that A transpose A, the Gram matrix, is non-singular, so you can take its inverse, and it's about projecting. And I must say, this is the first time I'm teaching it this way, because this is not the way you'll see it in the VMLS book, but it's rather the way you'll see it in Gilbert Strang's books, in the Introduction to Linear Algebra, etc. So the alternative way is probably more enlightening, and I think in retrospect, next year I'll start with this way, assuming I teach this next year. I won't see any of you because you'll all pass. And that's using least squares. And if we're thinking about least squares, then what we're thinking about is we have, again, the system of equations that we want to solve, AX equals B, but we can't because we're not lucky enough that B is in the column space of A. So there's no solution. So if you don't have a solution, what do you look for? You look for an approximate solution. You say, what would make a nice approximate solution? So there's a nice approximate solution. Let's, instead of AX equals B, let's just write AX minus B equals 0. Right, AX minus B equals 0. And what would we like for AX minus B? To be exactly 0, but it can't be exactly 0. So let's make it AX minus B as small as possible. So let's make this error as small as possible. And that's similar to what we did in the projection. So how are we going to make this error as small as possible? Well, let's minimize the norm. Let's find the x that minimizes the norm, or let's think of the norm squared. So if we minimize the norm, it's just like minimizing the norm squared. So then we have a minimization problem in x. You see? We have a minimization problem in x. Okay. So once we have a minimization problem in x, A is fixed, B is fixed, you want to minimize the x. So you can even do this and plot. Here you have A which is 25 by 2. Okay, A is very skinny, 25 by 2. And B is a vector, it's 25. Okay, so you've got 25 equations here. You've got 25 equations with 2 unknowns. I mean, 25 equations with 2 unknowns, you need to be bloody lucky to have an exact solution. So you don't have an exact solution for 25 equations with 2 unknowns. So you minimize this thing. So if you minimize this thing, let's call this thing the loss. So loss. How much we lose for every x1, x2. x2 is like the choice of x. Okay, that's the loss. So the loss is the norm of ax minus b squared in this case. Okay. If, by the way, if it's not squared, those contours of the loss will look the same. They'll just have a different meaning. Okay, because squaring is a monotonic transformation for positive numbers. And this is now a contour plot of the loss. So the loss, even though you've got here 25 A's and 2 B's, etc. Okay, so the loss is just a quadratic function, actually. Okay, we'll get to something called quadratic forms later on in the course, Okay, the loss is nothing but a quadratic form. It's like a generalization of a parabola. So here you see it plotted, right? These are contour plots. And this point here, right in the middle, is the minimization of the loss. Minimization of the loss. So if we want to minimize the loss, let me give you first just the solution before we do this, because we won't manage to do derivatives and things like that this week for it. So the minimization of the loss, you want to minimize A and B. All you want to do, you want to minimize this loss, okay, not A and B. You want to minimize X, so you want to minimize A and B. All you want to do now, connecting it to what it was before, all you want to do is you want to project B onto the column space of A. So X hat is nothing but A dagger of B. Okay. X hat is nothing but A dagger of B. So what you do is X hat is A dagger, or the pseudo inverse of A, times B. And this thing is, look, this is at a point minus 8.6, 8.91. Sorry, maybe it's, I didn't run this code. So we'll get a different A hat. We'll let this run. So X hat is going to be the minimum point of that. Okay, I'll plot it for you in a second. Now, unfortunately, today, I'm not able to show you this to kind of motivate you, but when you're actually fitting a line through a cloud of points, you're doing the same thing. We'll see this after the quiz next week. Okay, that will be like the big application. So here's X hat. So you see X hat is at, let me actually plot X hat. So I'll put X hat here. Let's do X hat here. And let's do a show X hat. And let's do plot of X hat 1, comma X hat 2, or scatter maybe. Scatter exclamation mark with color equals red. So this, it didn't like it. X hat, why not? Oh, maybe just scatter X hat. That didn't work. So let me see a second. X hat. X hat is a 2-element array. All I want is just to put, oh no, this should have worked. X hat 1, comma X hat 2. I think this may be like that. That's annoying. Whatever. This will just plot this minimum point. Okay. Legend equals minimum point. Label equals minimum point. So this minimum point here we got by the pseudo inverse times P. So it's exactly what we did before. Well, what I'm showing is now if your minimum, it's like, let me relate this to the notebook just so you. So when we did all this stuff here, you know, we could have had the point here, we could have had the point there, we could have had the point in different spots. So as I put this point, the magnitude of this error, the norm squared of this error grows, and it actually grows quadratically. So when I'm actually moving these points around, the error grows. So what you just saw in Julia was a plot of this point, and in this case, you're just projecting onto 2 dimensions, okay? A plot of this point as you change X hat, okay? Or a plot of the loss, okay? And the loss is minimal here. Okay, any questions about that? Okay, so now, by the way, I have a visit hour tomorrow. and I have a visit hour Friday, and few have come to the visit hours. So visit hour, like consultation hour via Zoom. These are not recorded, and you can ask their things and non-anonymously, etc. So feel free to come. Okay, so let's just do a bit of a summary of what we've seen today. So we've got A dagger. I'll just write it like formulas. Is A transposed A inverse times A transposed. Okay. And we've got P is A dagger, which of course would just be an A times A transposed A inverse A transposed. Okay. These were the two main matrices. Okay. So when we go to a system of equations like AX equals B, that does not necessarily have a full solution, a solution, okay? Because B is not in the column space of A, then what we can do is we can say X hat is going to be A dagger times B, okay? That is the approximate solution. But it's a very good approximate solution because it actually minimizes the least squares. And we can say, you can call it if you'd want, B hat, or just P, that's what we called it before, is A times X hat, which is the big matrix P, the projection matrix P times B. Okay, that's what we do. Now, just to close in the last few minutes, let's connect this to the QR decomposition. Okay, the QR decomposition. All right, and let's enjoy sticking QR inside each of these matrices and see what happens. Okay, so with QR, if we have A, which is again assume it's skinny full rank. When I say skinny, it can also be square. Okay. All right. Now, by the way, if A is square full rank, before that, very, very quickly, if A is square full rank, then look at A dagger. If A is square full rank, A is n by n full rank. Okay. A dagger is A transposed A inverse A transposed. Now, you can then apply the inverse to each of these guys. Okay. And you will say it's A inverse, A minus transposed inverse, A transposed. You couldn't do that before. You couldn't do that before. Okay, A transposed. And then these two guys cancels. You couldn't do it before because A has to be square. Yeah, the square, n by n. And then these two guys cancel. So the pseudo inverse is just A inverse. Okay, so the pseudo inverse, the Moore-Penrose pseudo inverse, is just A inverse when A is square. Okay, this is for A square. Okay, so it's really a generalization of the inverse. Okay, but now let's look at this formula with QR decomposition. Let's look at it with QR decomposition. So we have the matrix A, it's skinny full rank. That means its columns are linearly independent. That means it has a QR decomposition where R is upper triangular and Q is a matrix with orthonormal columns. So let's see what happens. Let's see what happens. So we have A dagger is QR transposed. That's this A transpose here. Okay, times QR. All of this inverse times QR transposed. Okay. Let's play with it a bit more. That is R transposed, Q transposed, because the transpose flip these guys, times Q times R inverse, and here why not do an R transpose Q transpose. What happens with Q transpose Q? What happens with Q transpose Q? It becomes the identity. Good. All right. So then we got R transposed identity. So I don't write it. R inverse. R transposed Q transposed. Now A was skinny full rank. R is a square matrix. And it has, it's non-singular because it has all the diagonals. The determinant, which is the product of the diagonals, is not zero. All the elements in diagonals are not zero. So R is invertible. So then you can write R inverse, R minus transposed inverse, R transposed, Q transposed. Okay. So finally, you can cancel these two guys because they're the identity. So you get R inverse Q transpose. So the pseudo inverse, when you look at the QR factorization, and that's actually how pseudo inverses are typically calculated algorithmically via QR factorizations, is R inverse Q transpose. Okay, R inverse Q transpose. And that's it. That was one application of QR into this. The second one, try this yourself. Stick here a QR factorization and make everything cancel. See what you get. See what you get when you do a QR factorization in terms of the projection matrix. Okay, which is just almost like multiplying this thing by an A on the left or by a QR. Okay. I really feel I might have overloaded you a bit, but I don't know what to say. No, but any questions? No? Okay, everybody. So are you asking about the P transpose? No, it'll be QQ transposed. Yeah. So if you now look at the matrix P, the projection matrix is A times A dagger. So that is A times this R inverse Q transposed, but the A also has a QR factorization. So that's QR R inverse Q transposed. So that's Q transpose, so that's Q transposed. So this is important. So Q transpose Q gives you the identity. QQ transpose doesn't give you the identity, it gives you a projection. Okay. Okay, good luck preparing for the quiz, finishing the first homework. Feel free to visit the consultation hours, ask questions on Piazza, stay positive. You're in the heart of semester. Keep in mind, this course does not have a final exam. So we work a bit more during the semester, and for the instead of final exam, you have a project which will hopefully not require as much. Have a good afternoon or evening. Bye-bye. Oh, yes. Will you get quiz grades soon? Yeah, you were going to get them today, but I simply did not manage. Too many kangaroos and snakes. You will get them by tomorrow night. Quiz grades you'll have by tomorrow night. Okay, yes. See you. Bye-bye. Thank you. You too. So I'll just answer this question. A D by N in real-world data. D is a dim, N is a number of instances. Sorry, one last. I didn't understand the question. Ask it again. So a D by N in real data world. D is a dimension, N is a number of instances. How about come to the consultation? Do you want to ask it now?
I think just say in the course, say on the A, the normally, because what I work on the R or Python, normally the input, the number of input is put on the column. In the attribute, it's on the
oh, okay, okay.
It's not transposed, so it's a bit confused. Yeah.
Okay. Right. So there's like two ways of viewing a data matrix. Do you view the rows as like people, observations, and the columns as features, or vice versa? Today, I spoke about it as, well, I didn't speak much about data, But I spoke about the columns when I spoke about Gram-Schmidt. The columns were each observations.
It's observations, okay.
Sorry, columns were instances, and the rows were the features.
Different attributes.
Yeah, but there's really two ways to view this, okay, as natural.
All right, okay, that's interesting. All right, thank you.
Take care, see you.
Okay, see you, bye.
All right, I'll go. Bye, guys.